Hi everybody, Dermot O'Shea here, and I'm your host of the Antenna Podcast. And today I'd like to introduce you to our next guest. Oliver, do you want to introduce yourself?
Yeah, hello everyone. I'm Oliver Leisten. I'm the CTO of Helix Geospace in Abingdon, England, and I've got quite a long career, had quite a long career, so I'll try and be very brief. The situation was I graduated from Loughborough University in 1979. I was working actually as a sponsored student for Plessey Avionics and Communications at the time, and I was doing radio engineering, things like military radios and aircraft radios, things like that. But in 1983, I decided to take a break, and I I became a PhD student sponsored by Philips Research Labs, and the subject of my research was solid state microwave devices, which was very fulfilling. I finished that in 1989 and started what's turned out to be a very long career in satellite navigation, the GPS system. So I started with a company called Plessey Avionics, which shortly afterwards became GC Plessey Avionics. And I was working on navigation instruments for aircraft and also for ships. I was doing that until 1991, and then I changed work to work for an independent navigation company, then called Navstar Systems, and I worked on a receiver chipset for GPS. So you'll notice so far I haven't mentioned anything about antennas because I never had, at this stage in my career, I'd not even really thought about them very much. I certainly hadn't attended an antenna class, and
Mm. Loughborough does have, a good antenna
yeah,
expertise classes and offering there in their university, right?
yeah, that's right. Well, when I was at Loughborough, they didn't.
Okay.
Actually, at that time, they were very good at electromagnetic physics, but the main application was heavy machines, and what was then the Central Electricity Generating Board used to train their students in power generation. So power electronics was the main thing. And I suppose I was exposed to things like induction motors and so on. And if you think about an induction motor being an induced sort of spiral of conductors, I was thinking about electromagnetic physics, and it did lead to some thoughts about antennas later. But when I was actually developing a silicon chipset for GPS, and I must have worked on one of the first ones. We were challenged really in a very exciting industry that was developing a lot of IP to develop IP that we thought was useful. And I actually, as part of my PhD, had been exposed to dielectric waveguides. And I started thinking that, well, dielectrics can make very low loss components. You know, we all talk to each other through optical fibers, and they are very low loss. And I thought, well, maybe antennas could be made smaller. And that was the interesting thing about it, was that at that time, GNS antennas were really very large. They were, they were free space. They weren't dielectrically loaded. And so I thought, well, actually, this is where I think the intellectual property is going to be. And I started researching dielectrically loaded what were originally quadrifilar helix antennas, and I made them very small. I was finding my way in the antenna field at a time when the company wanted to divest of what I was doing, and I was given the opportunity to actually do a management buyout. And so in the year 2000, I started a company called Sarantel with an initial investment of £6 million from the main investor was actually 3i. That was quite a bold move, it turned out, because the big deal was how do you make them? And I'd made a business plan where I thought, I need to make these products very accurately because they are quite small. So I needed to develop laser lithography methods and laser trimming actually at the time, and also automated assembly methods. And all of that went into the business plan, but it took 4 years before we actually started developing products which yielded commercially. So Sarantel was this company, and it made 6 million antennas, but in fact it didn't make it through the financial crash because it was not able to raise enough money during the period when the banking sector was in a bad state. And so I then transferred the technology to a Japanese company called Marua and spent 3 years, very interesting years, working at Marua. So I learned something about how a Japanese team would make this type of product. And then I thought I need to have another go. And so I started my current company, Helix Geospace, and it's basically it's there really to take the antenna technology to the next level, more into multi-band types of antennas and very efficient antennas. So that's me. I brought you up to date.
And so interesting. So you didn't have the theory or the background. So did you kind of teach yourself antenna theory, or did you kind of like, realize you kind of knew how to design it just from experience with the radios and the dielectrics, or how did you fall into the antenna design in the first place, and how did you learn about it?
So I remember a lot of people around me were very skeptical about whether this was a good idea, and they used to say things like, well, how does the signal get out of the dielectric? Won't it be trapped? And antennas as small as that can't possibly be efficient. And I used to experiment with these things, and I said, well, okay, if it isn't efficient, then why isn't it getting hot? Where is the energy going? And I knew about things like the quality factor of the materials was very high. And but to be honest, I didn't really know what I was doing. I learned. I kind of learned on the job. It was a reasoned argument that these were going to work. And I suppose gradually I found ways of making them work quite well. But, that process was annoyingly gradual from my investors' point of view, I think, at certain times. Yeah.
Well, I've found myself over the years, investors find antennas a frustrating business, right? Because of the uncertainty, and there's no recurring revenue, and we have so many exciting applications and use cases that they're super cool, but don't go into high volume production. So it's like it's a minefield for investors, that's for sure.
Yeah, no, that's true.
But I remember where we probably first came across each other at Sarantel, and one of the key advantages that you had was resistance to detuning, right? Especially from the body and from other external factors. How did you achieve that with this quadrifilar antenna that you had invented?
Well, I mean, what I realized, in fact, you could take the case of an induction motor. You make a switching magnetic field, and you put a kind of a squirrel cage of conductors in it, and basically the induced magnetism in the stator causes it to rotate. That is how Tesla motors make their cars go, or trains work, electric trains. These are very, very, very powerful fields, the induced fields. And I suppose one of the things that I learned at university that surprised me was that when you make a wire circuit, the energy isn't in the wire, it's in the surrounding space. And that was surprising to me, because I used to get electric shocks and I was sure that the energy was in the wire until they told me it wasn't. And so the situation is that what I saw dielectrics doing was basically giving the space for the electric field of the resonance of there has to be resonance to create a lot of energy to radiate. That electric field could be parked in a space that didn't outreach to the human. And so I saw this as a big opportunity to make wireless devices more efficient near the body, and also the tuning to be less, if you like, affected by loading of things that are in close proximity. And I still feel this. I think there's a very great opportunity in it for humanity, basically, to make wireless devices that don't share much of the resonance field with the human body. I mean, it's obvious that if you lose the energy just making the user of the device hot, the energy is lost to the purpose of transmitting it to the other side of the link that you want to make the wireless link with. So, it is an attractive proposition if you can make that process more efficient, albeit at the cost of needing a dielectric core. I realized that, I suppose in a simple way, you could make all of the antennas on planet Earth smaller if you made the whole universe out of a dielectric medium, right? And everything would be smaller, but that would take a lot of dielectric medium. A much more attractive proposition is to make the core of the antenna small, and actually balance fields across it, knowing that the fields would then be mostly within that dielectric medium. And so that argues for the use of balanced fields. If you have balanced fields, you're going to be able to make the use of a dielectric material relatively cheap, because you'll not need very much of it. And so I was thinking along those lines, basically.
Okay. Well, it's fantastic that it's still, alive and kicking and got great future potential as a technology within Helix now. So I've seen some great use cases. As a competitor, came across it in the Golf GPS product in soldier radios. But like, what would you say is like the coolest application or project you've worked on, or the one you're most proud of?
Well, I'm still convinced that there's an enormous contribution, and it seems to grow every time you look. I suppose the proudest thing I've done is I managed to get um, a um, a project away with Iridium when they were developing their next generation of satellite telephones. Um, I actually got that work from a simulation. The simulation in those days was really quite a complex simulation because I was using meshes that were cubic, and they were you need a lot of cubes to represent a cylinder with a spiral on it. And the situation is that the simulation took 5 months to do. So I told Iridium that, I was going to simulate the product and hopefully I would make it work. And they'd get the answer in 5 months. And sure enough, it worked. And we got the business. And then we had to make a factory that could make multi-filer antennas. So, I made octofiler and then decifiler helix antennas for them. And today, those antennas are very attractive for the Iridium IoT type of business. And I'm, quite proud of that because I kind of predicted that could be so, and made certain I suppose, modifications to the core technology to make it have the gain bandwidth that was very suitable for Iridium. But, more recently, I've been convinced that the use of dielectric cores is very important for arrays because when you're making arrays, your enemy is the coupling between members of the array, the individual elements of the array. And those couplings can be very strong because they can be comprised of near field or resonance fields. And if you can make the outreach of near fields or resonance fields very small with a dielectric core, you can reduce those couplings, but at the same time make the focal behavior of the fields sharper. And this enables you to make much better arrays. And actually, it's been a wonderful thing to be able to prove that in actual products. So, I'm now able to show that it does have a great there is a great opportunity. Sorry, I turn this. There is a great opportunity to make very good nulling arrays or beamforming arrays with this technology, and that's a coming theme in Helix.
Yeah, I've seen that on your website. You have the SERPA antenna. I presume that's what you're talking about there. And you can't be underestimated the challenge of doing Iridium antennas for IoT that are small and compact and need to be certified. I learned that the hard way myself, trying to use patch antennas for Iridium projects because they want good performance at low elevation angles, which is very difficult with the patch antenna. And I presume you must have got around that with your own technology.
Yes, so there are some advantages to so a patch antenna does present the problem that the low elevation performance is quite hard to achieve. Whereas when you have a greater height in the form of a helical antenna, it's much easier to achieve. But it's still quite important that the gain ripple close to the horizon is good as well. to get a satisfactory product for Iridium. And it really has taken quite a lot of time to make the antenna work well enough in terms of gain ripple to be at the level that we are now. So the situation is that it really is important, I suppose, to emphasize that a lot hinges on the manufacturing technology. The manufacturing technology has to be able to achieve very, very high accuracies to be able to be able to yield products with a very low gain ripple close to the horizon. But if you think about it, when you have a dielectric core, it's sort of worth the effort, because the good thing is that the close to the horizon gain isn't very significantly affected by nearby objects. So you're delivering a product that can realize that performance actually in the field, which is what people want.
Yeah, that's it. So very interesting, Oliver. So here on the Antenna podcast, we like to do a little deep dive into a technical topic. So I was going to ask you to pick one and maybe talk to that for the last few minutes of the show here.
Right. So a technical project. I mean, there are all of the unusual ones: tracking animals, tracking sea creatures, and when you as you'll know, Dermot, in the world of antennas, you kind of get an insight into what humanity does in all its weird and wonderful ways. And I suppose I can't really ever better, for me, the experience of when I made my first radio as a child and wondered about how this remarkable technology works, and just I've never really grown up in the sense that I still think it's wonderful. It never changes. But the idea that I think I just have to say that the idea that you could make antennas resonate so much smaller than their natural wavelength and still maintain the efficiency, still make them good enough for satellite links. It's something that seems counterintuitive, but it's true. And then when you think that comes with the opportunity to reduce the SAR, specific energy absorption rate, and increase the efficiency, reduce the coupling between antennas, it seems that there are so many advantages, which I suppose I just have to say, as a theme of antenna thinking, I have to consider myself very privileged, to have been able to spend so much very fulfilling. I spent years thinking there must be a snag. I must be wrong. This can't be this good. And the trouble is, if there is a snag, I still haven't found it. But that's I suppose that's the thing, that the antennas fulfill so many functions that picking one particular one, it is quite hard to do. They go into so many places, and each one is something which I consider to be very exciting and, in its way, very elegant. That's pick one. I suppose I'd have to go back to the Iridium case simply because it was such a punt. In my career, there may have been two of those. Actually, that was one. And the other one was when we could afford to send an antenna to Switzerland for SAR testing by the originators of the SAR testing method that became the DAISY system. And I sent it to them with an email saying that I suppose the minimum SAR would be in this direction. And 2 weeks later, I got the graphs back. It was precisely where I thought it would be. And that now wouldn't surprise anyone because CST can tell you that it would be like that. But my thinking in those days was based on analysis, so it was quite exciting.
Yeah, no, that's a great attitude to have, and I think, we joke about that a lot. Like you mentioned, the challenge with the investors and how long it takes to maybe make a return in the antenna business, and we always laugh that there has to be easier ways to make money, right? There has to be easier businesses than this painful antenna business from a profits perspective. But at the end of the day, I think everybody that works in it loves it, right? It's got so much variety, and there's so many. It's every day is a challenge, and there's every day is a school day. All the projects are different, and you get to meet some great people. So even though it's tough, it's rewarding, I think, at the same time.
Yeah, I think so too, and it's it's a great thing, and I hope that people will find a way to make it very profitable too.
Oh, well, some do, in fairness, you know what I mean? Some do.
Yeah.
There was one thing you mentioned I think we haven't heard before on the podcast was gain ripple. Maybe before we go, you could just give us a quick, explanation on gain ripple.
Right. So when you're communicating with a very low Earth orbiting satellite, if you think about the problem, if it's passing overhead with a low Earth orbiting orbit, you may actually be in contact with that satellite for 10 minutes. But a little pause for consideration, and you realize that actually most of that 10 minutes will be in the satellite rising or setting phase, and the passing overhead will be a very rapid transition. So it turns out that the low Earth orbiting satellite community want to have gain in the sort of 8 degrees above the horizon sort of dimension, and they want that whatever orientation the antenna is. So basically, that's a key parameter. When you make a circularly polarized antenna, to be able to achieve a very high, a very good gain ripple, it needs to be rather purely circularly polarized. If it's elliptically polarized, there is going to be a ripple, and it's going to manifest most at close to the horizon. That's because one dipole is smaller than another, and this is the issue. We want to try and make that ripple. We really need to make a cardioid in all directions, and so that, that's a key, if you like, skill in making small circularly polarized antennas, which requires accuracy. Our approach really is to isolate the antenna from the platform so that its characteristics are rather pure. They're not being influenced very much by radiations from the platform, and and we also need to make it very accurately. To make it isolated from the platform, it needs an integral balun, and so that is part of the configuration we make, and it does achieve the the performance advantages that we now can routinely deliver to that industry. It wasn't always the case. Our first antennas didn't have very good gain ripple. I can remember people arguing that we should specify the gain ripple close to the horizon at 12 dBs peak to peak. It needs really to be something more like 3 dBs peak to peak to be able to achieve the qualification standard that is required.
And how do you measure that? How do you measure gain ripple?
So you'd measure the you guys have got the perfect anechoic chambers for doing it. You measure the elevation, the azimuth at different angles of elevation, and like I say, for Iridium, the key one is 8 degrees above the horizon.
Okay.
Measure the azimuth at that elevation, and look for its ripple.
Okay.
Its radius ripple.
Very good. Very interesting, Oliver. I think we could talk for hours on this stuff. But if people want more information on some of the items we mentioned, you can check out Oliver's company website at helixgeospace.com, right?
Yeah.
And for more info. But for today, thanks a lot, Oliver. Great to have you.
Yeah. Thank you very much. I've enjoyed it, and it's been a great honor. Thank you.
Thank you.